Welcome viewers, in this video we will see the details about the Norton's theorem. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Norton's theorem, one of the theorem available in the circuit theory. Norton's theorem is the dual of the Thevenin's theorem. The Thevenin's theorem and problems are available in separate videos. In Thevenin's theorem, the Thevenin equivalent circuit is voltage source connected in series with the Thevenin resistance. In Norton's theorem, the current source is connected in parallel with the Thevenin resistance. That's why this Norton theorem and Thevenin theorems are called dual of Thevenin's theorem. Now we'll see the statement. Any linear active network with output terminals A, B as shown in the diagram can be replaced by a single current source ISC in parallel with the single impedance Z Thevenin or R Thevenin. So in this Norton's theorem, we are going to convert the complicated linear active network into simplified equivalent circuit. This is the linear active circuit, the AB, terminals AB. This is the load terminal. The load is connected across AB. In which we are going to find either load current or load voltage. This complicated circuit is replaced with short circuit current source. One short circuit current source in parallel with the Thevenin resistance. This is the load terminal AB. Right? So in Thevenin's theorem, we have Thevenin voltage V Thevenin in series with the R Thevenin. Here short circuit current source. There voltage source in series with the Thevenin resistance. Here current source in series with the Thevenin resistance. Now we'll see how to find the short circuit current and RTH. What is the procedure to find the short circuit current and RTH? ISC is the current through the terminal AB of the active network when shorted. We need to short circuit this terminal AB. Then we need to find what is the current flowing through the terminal AB. That is nothing but short circuit current. This is a current source. Right? So ISC is nothing but short circuit current by short circuiting the terminal A and B. Then Z Thevenin is the Thevenin impedance. Thevenin impedance means the impedance across AB when all the sources are removed, both current source and voltage sources are removed, the equivalent resistance across AB is nothing but R Thevenin or Z Thevenin. Right? So the complicated network with the terminal AB is converted into short circuit current source and Thevenin resistance. The short circuit current is nothing but current is flowing through the terminal AB when it is short circuited. And Thevenin resistance is resistance across AB when all the sources are removed. Right. Now we'll see the further description available in this network. The current through an impedance connected to the terminal of Norton's equivalent circuit must have the same direction as the current through the same impedance connected to the original active network. Right? So the condition is available. Current through the impedance connected to the terminal of Norton equivalent circuit should be same as the current through the same impedance through the original active network. Right? Current through the impedance, load impedance must be same as the current through the original network. Then only it is possible. After evaluating the value of ISC and RTH, the current through the RL connected across AB can be calculated by applying the division of current formula, current division rule as expressed below. Right? So after finding the ISC and R Thevenin, we have this final circuit is available. This is the short circuit current source, Thevenin voltage, Thevenin resistance and the load terminal AB. This load resistance RL, our aim is to find the load current IL. So because of this simplified network, we can easily find the current through the load resistance by using the current division rule. So the short circuit current is flowing. At this point, the current is divided. The current is flowing through the R Thevenin as well as RL. Current is divided here. So by using the current divider rule, we can find current through the RL, that is IL equal to, what is the formula? Total current multiplied by resistance of other network. What we need is current through RL. Other network is RTH. So it is multiplied by RTH divided by total resistance. RTH plus RL. Right? So IL equal to total current multiplied by resistance of other terminal divided by total resistance. In case of voltage divider rule, the resistance of the same network, same arm will be available. Here resistance of the other arm, right? What we need is current through RL means you have to multiply with RTH. In case of voltage, the same resistance is multiplied, right? So by using the current divider rule, we can easily find the current flowing through the load resistance RL, that IL can be calculated. So in the Norton's theorem, the complicated network is converted into current source in parallel with the Thevenin. From that simplified circuit, we can easily find the load terminal AB. Either current or voltage through the load resistance can be easily calculated using the current divider rule. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the Norton's theorem contain DC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Obtain the Norton's equivalent circuit of the terminal A and B for the network shown below. So the network is available. We need to find the Norton's equivalent circuit. So here we have 100 voltage source is available. Voltage source 100 voltage is available. Another voltage source 20 voltage is available. This is 1 ohm, 10 ohm, 2 ohm, another 10 ohm is available. This is the terminal AB. Normally it is called as a load terminal. Here in this problem only we need to find the Norton equivalent circuit. Further there is no calculation. Only Norton equivalent circuit is needed. Between the terminal AB, normally it is treated as a load terminal. So the Norton equivalent circuit is nothing but short circuit current source. One current source in parallel with the Thevenin resistance with the terminal A and B. This complicated circuit should be converted into current source in parallel with the Thevenin resistance. How to find this current source? This current source is nothing but this is the short circuit current. That is terminal A and B is short circuited and we need to find what is the current flowing through this terminal A and B. That is nothing but ISC. Then Thevenin is nothing but the resistance between A and B. By removing this voltage source, either voltage or current source should be removed. Here two voltage sources are available. We need to remove the two voltage sources and we need to find what is the resistance across A and B is nothing but Thevenin, right? So we need to find short circuit current across the terminal AB flowing through the terminal AB, then Thevenin across the terminal AB. So first we will find the ISC. Step 1 is nothing but finding the current ISC. To find short circuit current ISC by short circuit the terminal AB. This terminal AB is short circuited, right? Now we need to find what is the current flowing through the AB. So we will take, this is the loop method, KVL, Kirchhoff's voltage law, using the loop method. So this is the first loop. Loop means closed circuit. This is the another closed circuit. The current will not flow through the 10 ohm because here the short circuit is available. So the current will try to flow the shortest path, short circuit path. So current will not flow through the 10 ohm, right? So this is the first loop. Current flowing through the first loop is I1. This is the second loop. Current flowing through the second loop is I2. Since AB terminals is short circuited, current through 10 ohm is 0. There is no current flowing through the 10 ohm resistor. So the short circuit current is nothing but I2. The current I2 is flowing through this. That is nothing but ISC. So short circuit current is equal to the loop current in the second loop I2. Right. How to find this current I1 and I2? We will follow the matrix method. This is voltage matrix, current matrix and resistance matrix. V equal to I into R. Right. This KVL method separate videos are available. First we will find the resistance matrix. This is R11, R12, R21, R22. What is R11? The total resistance available in the loop 1. The loop 1 ohm is available and 10 ohm is available. So 1 plus 10, right? This R12 or R21, that is nothing but the resistance commonly available between first loop and second loop. So this 10 ohm is available in both loop 1 as well as loop 2. So that should be written in negative. Other than diagonal, all elements are negative. So minus 10, minus 10. R12 as well as R21. Then R22. R22 is nothing but resistance available in the second loop. This is the second loop. What are the resistance available? This 2 ohm and this 10 ohm, right? Another this 10 ohm, 2 ohm, another this 10 ohm also available, right? So this is the resistance available in the second loop. 10 plus 2 plus 10, right? It is 10 plus 2 plus 10. Then the current is I1 and I2. The voltage available in the first loop is 100 voltage. The loop 1 100 voltage is available. In the second loop is a 20 voltage is available. This 20 voltage, right? So voltage matrix, current matrix and resistance matrix. I will go for the further simplification. So this 10 plus 1 11, minus 10, minus 10 22. 10 plus 2 plus 10 22, right? So while calculating resistance we need to take it into account. But the current is not flowing through the 10 ohm. But while calculation this 10 ohm also taken into account. So this is nothing but the delta value, del value, right? So del is nothing but 11 into 22 minus of minus 10 into minus 10, right? So 11 into 22 is 242 minus 100, 10 into 10 100. So these two negative got cancelled, but already one negative is available. So 242 minus 100 is 142, right? Now we will find delta 2. Delta 1 is not needed because the short circuit current is I2. So the delta 2 is enough. No need to find delta 2. Delta 1. What is delta 2? The second column should be replaced by the voltage matrix. If you replace first column with voltage matrix, delta 1. Second column by voltage matrix is delta 2. Right? So 11 minus 10. This second column is replaced by 120 voltage matrix. So 11 into 20 minus of 100 into minus 10, right? So 11 into 20 is 220 plus 2 negative 2 times available. So it becomes positive. 100 into 10, 1000. So it is 1220. So delta 2 value is 1220. So the short circuit current ISC or I2 is nothing but delta 2 divided by delta. 1220 divided by 142, that is 8.5 ampere. So we calculated the first value, short circuit current, that is the current flowing in the second loop I2 is 8.5 ampere, right? Now we will find the R Thevenin across the terminal AB. So what is R Thevenin? The resistance available between A and B. These voltage sources are removed now. This voltage sources removed. The equivalent resistance available A and B is nothing but the Thevenin resistance, right? So see this, at this point the current is divided, right? Here also again current is divided. So 1 ohm and 10 ohm are connected in parallel. We need to refer the resistance from this side onwards, not from this side, right? We need to flow, current is flowing here, so it is divided here. Again it is divided, so that 1 ohm and 10 ohm are connected in parallel, right? So 1 ohm and 10 ohm are connected in parallel. So R equivalent equal to R1 into R2 divided by R1 plus R2. That is 1 into 10 divided by 1 plus 10. So 10 divided by 11, it is 0.91 ohm, right? Now these two resistors are simplified with the value 0.91 ohm. Now we'll go for the further simplification. So for this 0.91 is now redrawn. Now the circuit is become like this, 10 ohm, 2 ohm and that equivalent to parallel resistance are become 0.91. So from here we can identify that these two are connected in series. At this point current is divided, right? So this 10 ohm, this 2 ohm and 0.9 ohm same current is flowing. That means these two are in series. That is parallel with the 10 ohm, right? 0.91 ohm and 2 ohm are connected in series in parallel with the 10 ohm resistor, right? So that this 2.91 is parallel with 10 ohm. So R1 divided by R2, R1 into R2 divided by R1 plus R2. 2.91 into 10 divided by 2.91 plus 10. So that it is 29.1 divided by 12.91. That is equal to 2.254 ohm. So the Thevenin resistance is 2.254 ohm. Now we got the short circuit current as well as the R Thevenin. So from that we can draw the Norton's equivalent circuit, step 3. So this is a short circuit current source in parallel with the Thevenin resistance. So the current source is 8.5 ampere. The Thevenin resistance what we calculated 2.254 ohm. So this is the Thevenin equivalent circuit with the terminal A and B. There is no further calculation. Only the equivalent circuit is necessary asked in the question, right? So in this problem, the complicated circuit we converted into Norton equivalent circuit. That is current source in parallel with the Thevenin resistance. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the Norton's theorem with the DC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. The problem is find the voltage across the 15 ohm resistor using the Norton's theorem for this circuit given. So this is the terminal AB. 15 ohm is connected. We need to find current flowing through this 15 ohm resistor. The circuit we have two voltage source available, 75 voltage, 20 voltage source, and this 60 ohm, 75 ohm, 30 ohm, and this 15 ohm is a load resistance. So this complicated circuit should be converted into Norton's equivalent circuit. The Norton equivalent circuit have short circuit current source, short circuit current, one current source connected in parallel with the R Thevenin. Then how to find the short circuit current? The terminal AB is short circuited. Then current flowing through the terminal AB is nothing but ISC. R Thevenin is nothing but the resistance across the terminal AB by removing the voltage sources. Either voltage or current source. Here only voltage sources are available. We need to remove the voltage source and we need to find what is the equivalent resistance across AB, that is nothing but a R Thevenin. So that this complicated circuit now simplified with one current source parallel with one resistance. This is terminal AB, that is terminal AB with 15 ohm resistor. So after simplified circuit, we can easily calculate the current flowing through this terminal AB because two resistors are available, one current source is there. So by using current divider rule, at this point current will be divided. By using current divider rule, we can easily find the current flowing through the terminal AB, that is nothing but load resistance 15 ohm resistor. So that is the aim of this Norton circuit. Complicated circuit is converted into simplified Norton equivalent circuit. Now we'll see that. $75 voltage is the ideal voltage source. 60 ohm resistor can be removed without altering the performance of the circuit. The resultant circuit is right. So this 75 ohm is available. So we can remove this 60 ohm because it is the 75 ohm is ideal voltage source, right? So voltage is not dropped across 60 ohm resistor. That is the ideal. Normally voltage source in series with the resistor will be connected. In current source parallel with the resistor will be connected. So any resistor connected across the voltage source, we can remove it, right? So 75 voltage is the ideal source. So 60 voltage can be removed without altering the performance of the circuit, right? So after removing, this is the equivalent circuit. Now we need to find first step ISC, short circuit current. The step 1 is to find the short circuit current ISC, that is the terminal A and B is short circuited and we need to find what is the current flowing through the terminal A and B, right? So this resistor is removed and the A and B is short circuited. So by using the loop method, KVL, Kirchhoff's voltage law, we can find the current. So this is the first loop. Current flowing in the first loop is I1. This is the second loop. Current flowing through the second loop is I2. So the I2 is nothing but ISC. Both are same. This I2 is flowing in the second loop. So current flowing through the AB also I2. So I2 is equal to ISC. Both are equal. So we need to find I2. From that we can easily I2. If you calculate I2, that is nothing but ISC. So by using this loop method, we can frame the matrix format. So this is voltage matrix, current matrix and resistance matrix. V equal to I into R. This resistance matrix is nothing but this is R11, R12, R21, R22. R11 is nothing but resistance available in the first loop. This is the first loop. What are the resistance available? 75 ohm and 30 ohm. So 75 plus 30. R12 and R21 is nothing but the resistance between first loop and second loop. R12 or R21. So this 30 ohm is available between first loop as well as second loop. So minus 30. Other than diagonal, all elements are negative. So minus 30, minus 30. Commonly available between loop 1 and loop 2. Then R22. R22 is the resistance available in the second loop. In the second loop only 30 ohm is available. Right. The current is I1, I2. Current in the first loop I1, second loop I2. Then this voltage. The voltage in the first loop is 75 ohm available and 20 ohm also available. Both are connected in opposed. So 75 minus 20. In second loop, the only 20 voltage source is available, 20. Right? So after simplification, 75 plus 30 is 105, minus 30, minus 30, 30, I1, I2, 75 minus 20, 55, then 20. Right? So this is the form. Now we need to find the delta value. This is nothing but delta. Right? KVL method separate videos are available. Delta equal to 105 minus 30 and 30. So we need to find the determinant value. 105 into 30 minus of minus 30 into minus 30. Right? So 105 into 30 is 3150. 30 into 30 is 900. There are three negatives available. These two negative got cancelled, but this negative will be available. So 3150 minus 900 is 2250. Now we calculated delta value. Then we go for delta 1 and delta 2. Delta 1 means replace the first column with voltage matrix. Delta 2 is replace the second column with voltage matrix. But here only we need I2 because I2 and ISC both are equal. I1 is not needed. So we need to find only I2 so that we will calculate delta 2 value. Directly we can calculate delta 2 value. No need to go for delta 1. Right? So this is the first column. Second column is replaced by the voltage matrix. 105 minus 30, 55, 20. This is nothing but the second column replaced by the voltage matrix. So 105 into 20 minus 55 into minus 30. So 105 into 20 is 2100. Here two negatives available, so it become positive. 55 into 30 is 1650. So by adding this we got 3750. Delta 2. Delta 1 is not needed. So I2 is nothing but ISC is equal to delta 2 divided by delta. So 3750 divided by 2250, that is equal to 1.67 amperes. So the short circuit current in a equivalent circuit, we need short circuit current, that is nothing but 1.67 ampere. So in the second step we need to find the R Thevenin value. R Thevenin. We'll find the R Thevenin value. How to find the R Thevenin value? R Thevenin is nothing but the resistance across A and B. All the sources should be removed. After removing all the sources, we have 75 ohm and 30 ohm. So we need to find the resistance from this end. So the current is flowing through this. At this point current is diverted, so that the 75 and 30 ohm are connected in parallel. 75 and 30 ohm are connected in parallel. So that R Thevenin equal to RAB equal to R1 into R2 divided by R1 plus R2. That is 75 into 30 divided by 75 plus 30. 2250 divided by 105, that is equal to 21.43 ohm. So R Thevenin, that is the resistance across RAB, is 21.43. So now we calculated short circuit current as well as R Thevenin. so that we can draw the Thevenin equivalent circuit, then we can calculate the load current. So the step 3 is to draw the Norton's equivalent circuit. So this is the short circuit current 1.67 ampere what we calculated. This is the R Thevenin 21.43 ohm what we calculated now. So this is the load terminal 15 ohm. So our aim is to find the voltage, the aim is to find the current flowing through this 15 ohm resistor. Current flowing through 50 ohm resistor can be calculated by the current divider rule, right? So I15 means current through the 15 ohm resistor equal to the total resistance, the total current 1.67 ampere into the resistance in the another network, other arm, that is 21.43 divided by total resistance 21.43 plus 15. In current divider rule, the total current multiplied by other branch resistance. Voltage divider rule means total voltage multiplied by same branch resistance. It is current means opposite. So that 1.67 into 21.43 divided by adding these two 36.43, that is equal to 0.982 ampere. So current flowing through the 15 ohm resistor. What is our requirement? To find the question is to find the current flowing through 50 ohm resistor is 0.982 ampere. So from this value we can find the voltage across. V equal to I into R. I is 0.928 ampere what we calculated now into resistance 15 ohm. So 14.73 voltage. The voltage is not asked, but we can able to find the voltage also, right? So in this problem, the given network is converted into Norton equivalent circuit, that is current source in parallel with the R Thevenin. Thereafter the load terminal is connected. So the circuit becomes simplified. The complicated circuit becomes simplified with one current source and two resistor. The current flowing through this resistor is a requirement that can be calculated by current divider rule. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video we will see the solved problem based on the Norton's theorem contain AC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. For the network shown below, determine the load current IL using Norton's theorem. We need to find the load current IL. So the network is available. The two AC sources are available. 10 voltage with 0 degree, 5 voltage with 90 degree. This is the load terminal AB. We need to find the current flowing through this 5 ohm resistor. It is termed as terminal AB. Here one inductor available J3 ohm. This side capacitor available minus 2J ohm. So based on Norton's theorem, this complicated circuit is converted into simplified circuit, that is current source in parallel with the R Thevenin. This is the load terminal AB. So the current source, this is called short circuit current. How to find the short circuit current? The load terminal is short circuited. Current flowing through the load terminal is nothing but ISC. Then R Thevenin is nothing but the resistance available between A and B by removing all the sources. The sources should be removed and find the equivalent resistance between A and B, that is nothing but R Thevenin. Then we have the load terminal AB. So that this complicated circuit is simplified with one voltage, one current source, resistance and load resistance. Thereafter we can easily calculate the current flowing through this load terminal AB by using the current divider rule. So our aim is to find the equivalent circuit, Norton equivalent circuit. So first we will find the short circuit current, ISC. So the step 1 is to find the short circuit current. To find short circuit current ISC, short the terminals AB. The terminal AB is short circuited. That is nothing but ISC. So after short circuit, we need to find the current flowing through this short circuit. Now we'll go with the loop method. So we'll consider this is the first loop. The current in the first loop is I1. This is the second loop. Current in the second loop is I2. So what is the current flowing through AB? I1 also flowing in downwards. I2 also flowing in upwards. So the difference between I1 and I2 is nothing but the current flowing through the terminal AB. I1 is current flowing in loop 1, I2 current flowing in loop 2. The commonly available, this load terminal AB, both I1 and I2 is flowing. So I1 minus I2 is the current flowing through AB. Now first we will consider the loop 1, right? So the loop 1 we have one inductor is available. So applied voltage equal to inductive drop. So 3J into I1 equal to 10 voltage with angle 0, right? So the voltage drop is 3J into I1. The applied the voltage available is 10 voltage. See the current direction here. Current is going from downwards to upward, right? That is from negative to positive. So that rise in potential plus positive, right? So 3J I1 equal to 10 with an angle 0 with a rise in potential. See the current is flowing like this in clockwise direction. So in clockwise direction means negative to positive. So plus. So from that I1 equal to 10 voltage divided by 3J. Now we need to simplify this. In order to find the I1 value, we need to simplify. So in order to remove this multiplied and divided by the term J, complex parameter J. So that 10J divided by 3J square. J square value is minus 1. We know that J square value is minus 1. So that 10J divided by minus 3. So that is nothing but 10 divided by 3 is 3.33. So minus J 3.33 ampere. That is the value of I1. Similarly, we need to find the I2 value. I2 value is this. Here also we have one voltage source and inductor is available. So applied voltage equal to, capacitor available. Applied voltage equal to capacitive drop. So minus 5 angle 90 degree. Why minus 5? See the current direction. It is downwards from positive to negative. So drop in potential. Here also clockwise only, but from negative, from positive to negative, going downwards. So that minus 5 angle 90 degree. Already in capacitor one minus is there. Minus J2 into I2, right? J2 is there, in that current flowing is I2. Now we need to go for the simplification of this value. So I2 equal to 5 angle 90 degree divided by J2. This J2 is brought in the denominator. Negative got cancelled, right? So is 5, this 90 degree is nothing but J. Here we multiplied and divided by the factor J, but here 90 degree, every 90 degree is J. So we can replace this 90 degree by J. So this J got cancelled. So 5 divided by 2 is 2.5 ampere, right? So I2 value is 2.5 ampere, I1 value is minus J 3.3 amperes. So from that we can easily calculate the short circuit current. Short circuit current is I1 minus I2. We already discussed in the network. It is clearly through the AB, I1 also flowing in downwards, I2 also flowing in upwards. Both the current directions are different. So that I1 minus I2. Minus J 3.33 minus 2.5. Right? This is I1, this is I2. So this is available in the rectangular form. That should be converted into polar form in order to get the magnitude and angle. So in the using calculator, you can directly convert. Otherwise, this formula is square root of minus 3.33 square plus minus 2.5 square. The real term and imaginary terms are squared, added and take square root. So that you will get the magnitude 4.164. Similarly, angle is tan inverse B by A. Tan inverse imaginary term divided by real term. So tan inverse 2.5. This 2.5 divided by 3.33, that is minus 126.89, right? So this value is not correct. This is imaginary term divided by this 3.33 divided by 2.5, right? The value, this value is correct, but this value is not correct. Minus tan inverse B by A. The imaginary term is 3.33, real term is 2.5. So 3.33 divided by 2.5, the angle 126.89. So that 4.164 with an angle of minus 126.89 ampere. This rectangular form directly converted into polar form using calculator. Otherwise, this is the formula. For magnitude, this is the formula. For angle, this is the formula. Tan inverse B by A. So now we calculated the short circuit current. So the second step, we need to find the Thevenin equivalent resistance RTH. RTH is nothing but this short circuit by removing the voltage source. To find RTH or equivalent R Thevenin or impedance, remove the voltage source by short circuit. While removing voltage source, short circuit. Current source means open circuit. So here one voltage source is there, short circuited. Here one voltage source, that also short circuited. So RTH is nothing but the resistance between A and B. This is the terminal A and B. See here, at this terminal the current is diverted through inductor and capacitor. Thereafter it is combined here. So these two are connected in parallel. Because of current is divided, we can easily say that this inductor and capacitor is connected in parallel. So R Thevenin equal to Z impedance, equivalent impedance is R1 into R2 divided by R1 plus R2. That is 3J into minus 2J divided by 3J minus 2J. So that is minus 6J square divided by J. So this J got cancelled, minus 6J. Right? So minus 6J ohm. This is the Thevenin equivalent. Now we calculated short circuit current as well as Thevenin equivalent. Now we can draw the equivalent, Norton's equivalent circuit. So the step 3 is to draw the Norton equivalent circuit. This is the short circuit current, Z impedance, that is R Thevenin or Z Thevenin, then load terminal. The current what we calculated 4.164 with an angle of minus 126.89 ampere. The R Thevenin or Z equivalent is minus 6J ohm. This is the load terminal AB with 5 ohm as a load impedance. Now our aim is to find the current flowing through this 5 ohm resistor. So easily we can calculate through by using current divider rule. So this current is flowing here. At this point current is divided. Some of the current will flow through this Z equivalent. Some of the current will flow through the 5 ohm resistor. So current flowing through 5 ohm resistor by current division rule. We can find by the current division rule. What is the current division rule? So IL equal to total current multiplied by other branch resistance, that is R Thevenin, Z Thevenin, divided by total resistance 5 minus 6J. In current divider rule, multiplied by other branch resistor. In case of voltage divider rule, multiplied by same branch resistance, right? So total current multiplied by other branch impedance divided by total impedance. So that minus 6J divided by 5 minus 6J, right? So this is given. This is the voltage current. Now we need to convert this into the rectangular form into polar form. So this polar form is minus 6 square. Angle is tan inverse B by A. Just now we saw that how to calculate tan inverse imaginary term divided by real term. Similarly here, the denominator we have 5 minus 6J. So square root of 5 square plus minus 6 square, tan inverse minus 6 by 5. B by A, real imaginary term divided by real term. So this is nothing but 36, root 36. Tan inverse this become minus infinite. So this is square root of 25 plus 36. Then tan inverse minus 1 by 2. Minus 6 by 5 is minus 1 by 2. So this is root of 36 is 6. Tan inverse minus infinite is minus 90 degree. So this is nothing but square root of 61 degree. Tan inverse minus 1.2 is minus 50.19. Right? Now we'll go for the further simplification. So these two should be divided. 6 divided by square root of 61. That is 6 divided by 7.8. Then minus 90. This is minus 50.15. So these two are multiplied, means these two magnitude can be multiplied and divided by 7.8. So it is 3.1988. These two angles are multiplied, means can be added together. Divided means subtracted. So minus 126 minus 90, while going the subtraction this become plus. So plus 50.19. So that we got minus 166.69. These two angles are added and this angle is subtracted. Multiplication mean angles are added, division mean angle is subtracted. So finally we got 3.1988 with an angle of 166.69 ampere. So we calculated the current flowing through the 5 ohm resistor. So in this problem the given complicated circuit is converted into Norton equivalent circuit, that is current source in parallel with the Thevenin. Then after converting this simplified circuit, we can easily calculate the current flowing through the load terminal by using current divider rule. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening. Welcome viewers. In this video, we will see the solved problem based on the Norton's theorem using AC circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic. Using Norton's theorem, find the current through the load impedance ZL. So this is the load impedance. It is termed as AB. The impedance is 5 plus J5. So in this Norton theorem, the complicated circuit is converted into Norton equivalent circuit. That is current source in parallel with the Thevenin or Thevenin. This is the load terminal AB. So after this simplified equivalent circuit, we can easily calculate the current flowing through the load terminal by using the current divider rule. Because this complicated circuit converted into only current source with resistance or Thevenin with load resistance. So current is divided. By using current divider rule, we can easily calculate the current flowing through the load impedance. This ISC is nothing but short circuit current is nothing but the load terminals are short circuited and current flowing through the load terminal is calculated, that is ISC. ISC is the short circuit current by short circuiting the load terminal AB. This Thevenin or Thevenin is nothing but the Thevenin, the impedance across A and B when all the sources are removed. Current and voltage sources should be removed and equivalent impedance across AB is nothing but Thevenin. So we need to find short circuit current and Thevenin. So first we will find the short circuit current. Step 1. Step 1 is the short circuit current. Step 1, to find short circuit current ISC. Short the terminals A and B. We need to short circuit the load terminal. That is called ISC. So after short circuiting, the current will flow through this short circuit. It will not flow through this 10 ohm and this inductor and this resistor and inductor, because the current will flow shortest path. So that this circuit now simplified as this voltage source with the 5 ohm resistor. This can be eliminated. The current is not flowing through this, so that we can eliminate. The current will flow through only the short circuit. So that what we have 100 voltage with 0 degree voltage source is there, 5 ohm is available. So current is directly we can calculate. I equal to V by R. 100 with an angle 0 divided by 5, so that it is 20 with an angle 0 ampere. So 20 ampere with angle 0. Now next we will find the Thevenin. Thevenin or Thevenin. So Thevenin is nothing but the Thevenin across the impedance across A and B with the source is removed. Now that the source is removed, the voltage source is removed. After removing voltage source, we need to find what is the equivalent impedance across AB, load terminal AB. So by seeing this diagram, we can easily say that at this point current is diverted. So these two are in parallel, right? This 5 ohm is parallel with 10 ohm plus 10J, resistor and inductor. These two are connected in series, that is parallel with 5 ohm. Right? So these two are in parallel. So that R1 into R2 divided by R1 plus R2. R1 is 5 ohm. R2 is 10 plus 10J. So that 5 into 10 plus 10J divided by 5 plus 10 plus 10J. Right? So it is multiplied 50 plus 50J divided by 10 plus 15, 10 plus 5, 15 plus 10J. Right? So this 5 is taken outside. So that 10 plus 10J divided by 3 plus 2J. 5 got cancelled. Now this rectangular form should be converted into polar form. How to convert this polar form? This magnitude and angle. Magnitude is calculated square root of 10 square plus 10 square. Real term square plus imaginary term square. Tan inverse B by A. Imaginary term divided by real term. Tan inverse 10 by 10. Similarly here square root of 3 square plus 2 square. Tan inverse 2 by 3. Right? So by finding this value, it is square root of 200. this value is tan inverse 1 is 45 degree. This is 9 plus 4, 13. Square root of 13. This angle is 33.69. Now it is converted into the polar form. So from that we can easily calculate the value. So these two are divided. Square root of 200 divided by square root of 13 is 3.928. These two angle means divided means the angles are subtracted. 45 minus 33.69. Multiplication means angles are added. Division means angles are subtracted. 11.31. Again this can be converted into polar form, into rectangular form. How to convert this? This magnitude is written 3.928. That's cos of this angle, cos 11.31 plus j complex term. Again 3.928 this value into sine of angle, sine of 3.1, 11.31. This is the formula for converting polar form into rectangular form. Magnitude into cos of angle plus j magnitude into sine of angle. So that is 3.845 plus j 0.769 in the rectangular form. Right? It is available in rectangular form. By using calculator we can directly convert polar form into rectangular form also. Now we calculated short circuit current as well as Z equivalent. Now we will go for the equivalent circuit. So step 3 is to draw the Norton equivalent circuit, short circuit current, Z equivalent and load terminal. The short circuit current what we calculated 20 with angle 0 ampere. The Z equivalent is 3.845 plus j 0.769. Right? Then the load terminal AB having the load resistance as load impedance is 5 plus j5. So this is available in rectangular form, so that Z equivalent also written in rectangular form. So our aim is to find the current flowing through this load terminal. How to find this? By using current divider rule. This 20 ampere is flowing. At this point current is divided. So by using current divider rule we can find the current through the load resistance. So IL equal to total current multiplied by other branch resistance. The current what we need is this 5 plus 5j, but we need to multiply with other branch resistance 3.845 plus j 7.69 divided by total impedance. We need to add both 3.845 plus j 7.69 plus 5 plus 5j. Right? Total current multiplied by other branch impedance divided by total impedance. In case of voltage divider rule, total voltage multiplied by same branch impedance. Current divider means other branch impedance. Right. Now we'll go for the further simplification. So this 20 ampere is there. So these two are added together. 3.845 plus 5, 8.845. 0.769 plus 5, 5.769. So this can be converted into polar form. We already discussed the square root of real term square plus imaginary term square. Tan inverse imaginary term divided by real term. Similarly in the denominator also. Right. So after simplification we got 3.9211 angle 11.31. This angle. Simplification of this is 10.56. This angle is 33.11. Right. Now we can go for further simplification. So these two are multiplied, then divided by this angle, right? 20 into 3.211 divided by 10.66. So that we got 7.427. This angle multiplication means angles are added, divided means angle is subtracted. So 0 plus 11.31, that is 11.31 minus 33.11. So 11.311 minus 33.11, we got negative angle, minus 21.8 ampere. So this is the final value what we need. Current flowing through the load impedance is magnitude is 7.427, angle minus 21.8 ampere. So in this problem we calculated the current flowing through the load impedance using Norton's theorem. The given complicated circuit is converted into Norton equivalent circuit. Short circuit current with the impedance Z Thevenin connected in parallel. So by using current divider rule we can easily calculate the current flowing through the load impedance. Subscribe the channel for more videos and notification. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.